Actifuse represents a new class of bone graft substitute. This unique material has been designed to address the many shortcomings of existing bone grafts. Here we see an Actifuse granule lying in blood. As we fly into the granule itself, the patented structure is revealed. Large macropores and smaller micropores are totally interconnected to facilitate bone growth throughout the graft. As we follow the migrating cells, you can see how the surface of Actifuse is also porous at a microscopic level. This strut porosity allows the material to adjust to pressure differentials and offers nutrients and cytokines a pathway from one side of a granule to another. The truly unique feature of Actifuse is its altered surface chemistry. The silicate substitution shown by the blue tetrahedra increases the negative surface charge on the graft. This changed surface chemistry has a profound effect on the commencement of the bone formation cascade. The first stage of bone formation is protein adhesion. There are thousands of different proteins in serum, and only those proteins possessing the RGD peptide sequence are relevant for bone cell attachment. In Actifuse, the negative surface charge attracts more of these cell attachment proteins out of solution and causes them to adhere to the graft surface in the correct conformation with their RGD sequence available for cell attachment. Here we see the RGD sequence of the protein. The negative charge attracts the protein towards the surface of the graft material. It binds in the correct conformation, allowing space for many others to join. By contrast, the reddened areas represent a material without a negative surface charge, and in this case you see how the proteins adhere differently, preventing optimal cell attachment. Pre-osteoblast cells passing by are drawn to the adherent protein layer. The cell's attachment points move, making themselves available to the adhered proteins at the surface. Where high protein concentrations are present, there are more attachment points, and so the cells are attached at a faster rate and in higher numbers. As the cell binds to the protein, filopodia are extended from the cell membrane and the cells differentiate into committed osteoblasts, the bone-forming cells. Once attached, the osteoblasts proliferate, covering the material in a carpet of new bone-forming cells. As this is happening, optimum levels of silicate, shown by the blue tetrahedra, are released into the local environment, which further accelerates osteoblast activity. The osteoblasts then transition into cuboidal osteoblasts and start to produce extracellular matrix. In the first of the major steps of bone formation, extracellular matrix is produced beneath the osteoblast, causing it to lift off the surface and rise upwards. As more and more extracellular matrix is produced, osteoblasts become trapped within the growing matrix, forming osteoid. This then mineralizes into woven bone, the second stage of bone repair. If sufficient woven bone is produced, the grafted area and everything in it will be bound firmly in place, preventing movement. In a stable environment, osteoclasts, shown here by the multinucleated red cells, pass along the material surface, resorbing the newly formed woven bone. This is the commencement of bone remodeling. The osteoclasts are closely followed by a front of osteoblasts, which begin to build new, more functional bone. In this sequence we see a trough that has been resorbed by the osteoclasts being filled by a multiple layer of osteoblasts. As these osteoblasts mature, layers of highly structured lamellar bone are produced, which marks the third and final stage of the bone formation cascade. The dynamic continuum of bone remodeling is established, with older bone being removed and replaced by new bone, according to Wolff's law. Actifuse is a new class of synthetic graft material which speeds up the bone formation cascade. In summary, Actifuse leads to the production of more bone in less time.